So am I recording?
I don't see a red
Yes.
dot.
I do. Yes, you are.
All right, so
Okay,
let me
I see
start.
it. I see it now.
Let me start since I want to talk about polynomials, and there are a lot of polynomials in the universe. So, oops. It's supposed to get to 1. Okay. Oh, all right. So there's a completely superfluous word in the polynomial world called hyperbolic. There's something called hyperbolic polynomials. And the sort of a general definition of them is if you have a polynomial in n variables and you choose a direction e, this would be a non-zero vector. One says that this polynomial f of x is hyperbolic in the direction e. If you look at f of, so x is n variables and e is n variables, x plus t e. So this is really just now, if you fix x and e, this is a polynomial in one variable t. And if this only has real roots, then your polynomial f is said to be hyperbolic in the direction e. But I'm only going to consider real polynomials with real coefficients in one variable. And the only direction is in the direction along the x-axis. So hyperbolic just means all roots are real. But for some reason, people like to talk about hyperbolic polynomials for polynomials with real coefficients in one variable. So when I say hyperbolic, it just means a hyperbolic that has no complex roots. All of its roots are real. And if you have a hyperbolic polynomial, all of its derivatives are hyperbolic. And the easiest proof I know is the Gas Leuka Theorem, because Gas Leuka Theorem says if you have a polynomial with real or complex coefficients, and you take the convex hull of the roots in the complex plane, that convex hull contains all roots of the derivative. Now, if your polynomial to begin with only has real roots, then the convex hull is just an interval in the real line, and that contains all roots of the derivative. So all roots of the derivative are real. So for a hyperbolic polynomial, all of its derivatives are hyperbolic, which is just a curious application of convexity. Now, there's a kind of polynomial called a Jensen polynomial. So you start with any sequence of real or complex numbers, alpha, and you can construct what is called the Jensen polynomial of degree d. So it's going to be a polynomial of degree d and shift n. So this is this polynomial of degree d, whose jth coefficient is the binomial d choose j. And if there were no shift, this would just be alpha of j. N is a non-negative integer. If you shift by n, then your coefficients are alpha of n plus j. So this is the Jensen polynomial of degree d and shift n. And there seems to be, as in all of mathematics, Aleph Knot papers on the subject. And they've gotten attention in the last couple of years. Here's just a very simple example. If alpha of n, let's say, is 2 to the n, then you take the polynomial of degree d and you shift by n, it's this, which is this polynomial, if I did my arithmetic correctly, right? So that's just a kind of trivial example of a Jensen polynomial. A slightly less trivial example is the following. Oh, yeah, this guy is hyperbolic, of course, because the only root is -1/2. So these Jensen polynomials, for all degrees and all shifts, are hyperbolic. If you take a Jensen polynomial, so let's say I take the Jensen polynomial associated with some sequence alpha, and if I take the polynomial of degree d plus 1, and shift n minus 1, call this j. If I differentiate it, if I did my calc 1 correctly, the derivative of this Jensen polynomial is another Jensen polynomial times some positive number d plus 1.
Jensen for the same alpha is the point, yeah.
Oh, absolutely, yeah. Yeah, alpha is fixed. So what that says is, so we have this identity. If you differentiate a Jensen polynomial, you get another Jensen polynomial. I mean, the guy was Scandinavian.
Wait, wasn't there some coefficient that we forgot?
Yes,
Multiplying
there's a
by
d
d?
plus 1 in there. Thank you.
Right.
Where's the second?
I mean, if all you care about is the roots, it doesn't matter. But if you're interested in the actual exact polynomial, it's
Yeah, I mean, the principle is one should try to write down things that are correct. So let's see if this works. Yeah. Yeah. Which means if you take the Jensen polynomial of degree d plus n and shift 0 and you differentiate it, then you get this Jensen polynomial of degree d and shift n.
yeah, sorry to pest it, but again, you need that constant.
Yeah, there's a factorial in there now. Every time you differentiate, you get d plus 1, d, and so forth. Thank you. But the corollary of this is that if you take the 0 shift Jensen polynomial, so the j alpha d's with shift 0, if this is hyperbolic for all d, then all the derivatives are hyperbolic. And if you differentiate this guy, you get the n shift 1. So if you want to know whether the Jensen polynomials are hyperbolic for all d and all n, it's enough just to know it for all d and n equal to 0. So, okay, now for those amongst you who want a quick way to get your $1 million, you want to look at the zeta function, right? And if you know zeta times gamma times this power of pi, so this is the functional equation for the zeta function. You're using this lambda of s equals 1 minus s. And I want to look at something slightly different. I want to take this function at a half plus z times minus 1 plus 4z squared. So this has a nice Taylor series that looks like this. And the coefficients it's even, and the coefficients of z to the 2, the coefficient of z to the 2n is gamma n over n factorial. So I'm interested in this sequence of coefficients, the gamma n's. And so there's a theorem of Jensen and Polya, which says that the Riemann hypothesis is equivalent to proving that these Jensen polynomials are hyperbolic. That means all roots are real for all non-negative degrees d and shifts n. So let me just go back for a second. So I have these numbers defined by this function. And I look at the sequence of these gammas that defines the Jensen polynomials. And
yeah, I should mention that these can be computed without, without going through the zeta function. There's a explicit formula for them in terms of theta functions. An integral, nice messy integral, but yeah.
So evidently Jensen had some notes about this. I don't know if they were ever published, and Polya went through his notes and wrote a long paper on the subject, and which is the origin of this. And from the little lemma that I said earlier, that for any sequence, doesn't have to be this gamma, for any sequence alpha whatsoever, you have the Jensen polynomials are hyperbolic for all d and for all n. If you just know they're hyperbolic for all d and n equal to 0. So that's, so you just have to look at this. So this has been around now for maybe 100 years. And recently, meaning 3 years ago, Michael Griffith, Ken Ono, and Larry Rowland and Don Zagier proved that some of these Jensen polynomials were hyperbolic. And some people made a fuss about this, and others were more skeptical.
Yeah.
And there's a very interesting paper by David Farmer referring exactly to this paper of Giffen and company, the title of which is Jensen polynomials are not a viable route to proving the Riemann hypothesis. So, yes.
I mean,
So
that's
this-
not a theorem. That's just you know, he offers heuristics for that, but I don't think he actually proves anything.
Well, I mean, how could you possibly prove that? Because every true statement applies to every other true statement, right? I mean, it's
Yeah, exactly. But
Yeah.
he does make some good arguments. Yeah.
and very recently, a guy we all know who's spoken many times in the seminar, Cormac O'Sullivan, posted a paper on Archive on exactly this subject. And I asked him if he wanted to speak, and he said, well, maybe next year. He didn't want to do it this year. But someone who was logged on to one of these talks a couple of weeks ago was chatting with me afterwards, and he said, I know you're interested in polynomials now because you want to solve the Riemann hypothesis. And I said, absolutely not. I had no interest. First of all, I don't think this has any, my gut is that this is not the secret to, proving the Riemann hypothesis or disproving it, but I was just interested in polynomials. But I decided it's really immoral to talk about polynomials in a number theory seminar without mentioning this recent work about Jensen polynomials and their connection to the Riemann hypothesis. Bombieri also wrote a paper saying, or a little note, saying this is the greatest paper on the Riemann hypothesis in a long time. But he also hasn't solved it, so it doesn't really matter too much. All right, so then we get back to what I wanted to talk about, which is just baby stuff about polynomials. And I had spoken about Descartes' theorem, and I had spoken about the Boudin-Fourier theorem. And just for completeness, that is, there are the three basic theorems about localizing or counting real roots of polynomials are Descartes, Boudin-Fourier, and Sturm. So just as I say, for completeness, to tidy up the package, I was going to sketch a proof today of Sturm's theorem. So it's useful to be able to bound the roots of a polynomial, whether they are real or complex. So the simplest bound for the root of a polynomial is, I have no idea who, why, or when, or how these were proved. This is always called Lagrange of Estimate. If you take any polynomial with real or complex coefficients, monic, if you let m be the sum of the absolute values of the coefficients of the, not the monic terms, but all the other terms, then every root is bounded by, it's either less than 1 or else it's bounded by this number m. It's less than or equal to the max of one of them. And there's a kind of trivial kind of proof, right? If lambda is a root, you let lambda n be equal to this, you take the absolute values, and this is when, in the case when lambda is at least 1, so lambda to the I is at most, is less than or equal to lambda to the n minus 1, divide by lambda to the n minus 1, and you get this estimate. A somewhat better estimate is due to Cauchy, which is the following. You take your monic polynomial, instead of taking the sum of the absolute values of all the roots, you find the maximum absolute value of the roots. So you let A be, let's say, the max of the absolute value of of each coefficient. Then every root is less than 1 plus A. And one proof is almost the same as the proof of Lagrange's theorem. You start with lambda being a root. So, so put your lambda to the n on one side of the equation and divide by lambda to the n minus I, and you get this expression for lambda. And when you take absolute values, the AIs are bounded by A, and this is bounded above by a geometric series. So you get lambda is less than this, which gives you exactly that lambda is less than 1 plus A. I mean, that's the whole proof. There's actually a much more interesting proof. There's a famous theorem of Descartes, which gives you a bound for the eigenvalues of a matrix. And so if you take your polynomial and you write what's called the companion matrix, so with a minus sign, you put the coefficients of your polynomial as the polynomial of degree n, monic. So you get the x to the n term, you write your coefficients like as the negative of them as the nth column of your matrix, and the rest of the matrix is 0 except for ones on the subdiagonal. So for that matrix, the roots of the polynomial are exactly the eigenvalues of the matrix. And when you write down Descartes' theorem, you get exactly this Cauchy estimate, which is
the Cauchy estimate is what influences everything that one does in Diophantine approximations with respect to algebraic numbers. That's what the height of an algebraic number comes in. It's a very good measure, and that's I mean, certainly much better than Lagrange's, but that's probably the right one.
Yeah, but it's just and the proof is also very simple. I mean, it's nice, but someone had to observe it first, and right. Whether it was Cauchy or someone else, but it's very nice. Okay, so Sturm's theorem. So you may remember that Descartes' theorem gives you an upper bound for the number of positive roots of a polynomial with real coefficients. It says that the number is something like the variations in signs of the coefficients of the polynomial minus some non-negative even number. And that is for the number of roots counting their multiplicities. So the Boudin-Fourier theorem gives you a similar upper bound for the number of real roots of a polynomial, but between any numbers A and B, counting multiplicities. So it doesn't tell you how many different roots there are. It gives you this bound counting multiplicities, upper bound counting multiplicities. Sturm's theorem gives you the exact number of real roots in an interval, not counting multiplicities. So if Sturm's theorem in some interval gives you the number 7, that means in that interval, there are exactly 7 different roots. Each root has some multiplicity that can certainly be greater than 1. They're not necessarily simple roots. It tells you there's no error, there's no waffling, it's not minus some non-negative integer. It's the exact number of roots between some A and B. And I'm following the 100-year-old proof in Van der Waerden's algebra book. And Van der Waerden writes, well, this is actually, so we now turn to the computation of the real roots of a polynomial f of x. By computation, we mean, in accordance with the definition of real numbers, an arbitrarily close approximation by rational numbers, which strikes me actually as a very modern way to talk about it, finding the root of an equation. But yeah. So the and I should also say, I'm talking about polynomials over the reals, but as everyone points out, everything that I'm saying is true in any real closed field. It's just that normal people don't know of any real closed field other than the reals. But if you find one in your meanderings, and you wanted to know how to count the number of roots of a polynomial, Sturm's theorem and all the other theorems I talked about apply just as well. So there's something which I think we call Rolle's theorem, but van der Waerden calls Weierstrass's No-Stellensatz. And it simply says that if you have a function that's continuous between A and B, and if f of A is negative and f of B is positive, then there's a C between A and B where f of C is 0. And what's usually used is the converse of that, which is if you have an interval, if you have a continuous function defined on an interval, and the function is never 0, then the function is either always positive or always negative. It never changes sign on the interval. So that is really the useful fact. And what Sturm does, he uses a sort of a modification of the Euclidean algorithm. So if you had any two polynomials, f0 and f1, and you wanted to find their greatest common divisor by the Euclidean algorithm, you would take f0, divide by f1, and call the remainder f2. So Sturm calls the remainder minus f2. So at every step in this sort of modified Euclidean algorithm, he's writing the remainder as minus something, as opposed to plus the something. But this is still the Euclidean algorithm for any pair of polynomials f0 and f1. And at each step, the degree of the remainder is strictly decreasing, and it can't decrease forever. So you terminate with some non-zero polynomial f sub r, which is a greatest common divisor of the two polynomials you started with, f0 and f1. And we're going to let f0 be the polynomial with real coefficients whose zeros in an interval we want to count, and f1 will be the derivative. And this sequence of remainders, right, in this modified Euclidean algorithm, we call the Sturm sequence f0, f1, up to f sub r. So that's a sequence of non-zero polynomials that come from the Euclidean algorithm. And so, and the Sturm variation function counts the number of sign changes in this sequence at any point lambda. So Sturm's theorem says if you have a non-zero polynomial and f, and this f0 up f1 up, this is the Sturm sequence. So f0 is the function f, f1 is its derivative, and fr is the greatest common divisor of f0 and f1. If a is less than b, and f and a and a and b are not zeros, then the number of roots of f of x, not counting multiplicity, I mean, really the number of distinct roots between a and b is exactly equal to the variation at a minus the variation at b. Now, I occasionally ask myself, why is it in Descartes' theorem, in the Boudin-Fourier theorem, and in the Sturm theorem, that the answer for the number of real roots in an interval comes from counting the number of sign changes in some sequence? And the answer is, I haven't the faintest idea. I assume that someone somewhere, maybe one of you, can tell me why this sign variation function has the secret to the number of roots. And I have absolutely no idea why that is. I mean, obviously Descartes, and Descartes was not the first. He put it in his book, but it was in other mathematicians' work before Descartes. Somehow they looked at this alternation of signs function for some reason and came up with an answer. I just don't understand why this is the case. But it is the theorem. And it has, and it's infinitely important. It's also computable. I mean, it's easily and quickly computable. So it's the basis of Tarski's famous theorems on the decidability of elementary geometry. Let's make some observations about this. Suppose you have your polynomial f of x, and lambda is a root of multiplicity L. Let's say L is at least 2. or listen, L is at least 2. So you can write f of x, I'm going to call f of x f naught of x minus lambda to the L times some function g of x, where g of lambda isn't 0. And if you differentiate f naught to get f1, this is freshman calculus, maybe. It's x minus lambda to the L minus 1 times something. And this something, if you evaluate the something as lambda, you don't get 0. So you see that x minus 1 to the L minus 1 is the common divisor of f naught and f1. Therefore, an x minus lambda to the L is not a common divisor of these two. So x minus lambda to the L minus 1 divides fr of x. That's the greatest common divisor of the function in its derivative. That is the greatest common divisor of f naught and f1. And if I were to take this greatest common divisor, f sub r of x, and divide f naught of x by it, lambda will be a simple root of this, because here's my f naught, and I'm dividing out by something which is x minus lambda to the L minus 1. So I'm going to end up with something which is divisible by x minus lambda to the first, but not to the second power. So lambda will be a simple root of f naught over fr. Fr is the greatest common divisor. It will divide every polynomial in that sequence of remainders, what I call the Sturm sequence. And in fact, what I want to do, when I did my Euclidean algorithm modified as Sturm does by writing each remainder as minus something, I take every polynomial in that sequence and I divide it by the greatest common divisor, f sub r of x. So then you get a sequence of equations that come exactly from that Euclidean algorithm, but now this gr of x is equal to 1. Right? This is not a, gr of x is equal to 1. And now, for any number lambda that's not a root of fr of x, the original greatest common divisor, the number of sign changes in the sequence that I got after my division is exactly the number of sign changes in the Sturm sequence, because I'm dividing by fr of lambda, which is either positive or negative, but all of the signs of these will differ from these. They'll either be the same if what I'm dividing by is positive, or it will be the negatives if what I'm dividing by is negative. But the number of sign changes won't change. So the number of sign change. So if I call, let's say, SG of x, this sort of the Sturm sequence that I get when I divide by this greatest common divisor, the number of sign changes in the original Sturm sequence is exactly the number of sign changes in this modified Sturm sequence. And it's the G sequence that I'm going to look at. And so what follows now are just a number of technical remarks, and it's probably too technical, but someday, eventually, I will write this down and it'll be on archive, or you can just go to the source, and my source is basically Van der Waerden, but you can also find proofs in every book in algebra, certainly in Lang, for example. So the first observation is that in the sequence of G polynomials, there's no lambda, which is a root of consecutive polynomials. There's no polynomial Gj and Gj minus 1 for which lambda is a root. Because if this were the case, then Gj plus 1 is some linear combination of these two, Gj minus 1 and Gj, and it would be 0 at lambda. And you would just move along, you would get that Gi of lambda is 0. Lambda is a root of Gi, not just for I equal j minus 1 and j, but for every j up to r. But the rth polynomial is 1, so you can't have lambda equal to G of that be equal to 0. So no two consecutive polynomials in this sort of modified Sturm sequence have the same root. Now, I have this sequence of R+1 polynomials. And a polynomial has only finitely many roots. So if you take all numbers which are the roots of any of these polynomials, so yeah. So lambda, I should have used maybe a lambda here, but if I let capital lambda be the set of all real numbers that are the roots of any one of these, one or more of these polynomials. This is some finite set of numbers. And it partitions the interval from A to B into a finite number of subintervals. In each of those subintervals, none of these GI polynomials is zero. So by the sort of contrapositive of the Weierstrass-Nostellensatz, in every one of those subintervals, none of the polynomials changes sign. So the number of variations of sign within a subinterval has to be constant. As you move along the subinterval and you're looking at this VG of X, you have sequence of numbers. The numbers are changing, but their signs don't change. So this counting variation of sign function is constant in all these intervals. So the only time this variation of signs function might change is when you cross a D, which is the root of one or more of these polynomials.
They don't have to change when you pass, right? It can change, but it might not.
They can change, but the only possible change is when you pass through a root of one of the polynomials. So let's take a number D, which is a root of one of the polynomials, but not of the zeroth polynomial. So GI of D is 0 for some I between 1 and R-1. The GR polynomial is just the identical, is the constant function 1, so that's never 0. But if GI of D is 0, that means that, let's say it's positive, that means GI is positive, so the sign is constant at D and a little bit to the right and to the left in those adjacent subintervals. But each of those subintervals, the sign never changes because the polynomial is never 0. So if GI of D is 0, then the sign is constant at X equal D and for all X in the two adjacent subintervals. But suppose at some K between 1 and R-1, we know D is a 0 of one of these. So let's say it's a 0 of GK. So we know by the previous remark that no two consecutive terms of this sequence of G's are 0. So if GK is 0 at D, GK minus 1 at D is non-zero, and GK plus 1 at D is non-zero. And we have this relation from the Euclidean algorithm. So at D, this is 0. So this at D is minus this at D. So GK minus 1 and GK plus 1 must have opposite signs. Neither of them is 0. And if one is positive, the other is negative. So let's say GK minus 1 is positive. So GK minus 1 of X is positive for all X in the adjacent subintervals. And then GK plus 1 is negative at D. So it's negative in the two adjacent subintervals. And there's a remark that I made last week, and I'll make it again. If you have a 3-term sequence, and let's say the first term is positive and the last term is negative, no matter what GK is, it could be 0, could be positive, could be negative, there's exactly one sign change in this triple. And similarly, if K minus 1 is negative and the K plus 1 term is positive, no matter what GK is, there's exactly one sign change in this triple. So it follows that if you look at this triple, as you go across a 0 d of one of these functions, not the first one and not the G naught function, there's exactly one sign change. So the difference, there's no difference, right? I mean, if you had 3 changes and now there's 4, and over here you had 2 changes and now there's 3, in both cases, there's just a difference. There's no difference in the number of sign changes. That is the point. So this Vj of x function, the number of sign changes, has the same value. Actually, this is actually a little bit stronger than what I just said. This is better since I wrote it. The number of sign changes in the G sequence has the same value at x equal d and on the 2 subintervals adjacent to x equal d, whenever d is a 0 of a polynomial in the sequence, in the G sequence, other than G naught. So there's no change. So if you cross a d where G naught of d is not 0, as Moshe said a moment ago, there doesn't have to be a change, and in fact, there is not a change. So the last case to consider, and this also says that if you look at the number of sign changes of the sequence from G1 to GR, that in fact is constant on the entire interval. That doesn't change at all. So the only time there's a variation in this, counting the number of sign changes, is when you're looking at the difference between the polynomial G0 and the polynomial G1. So suppose you take d to be a root of the polynomial G0. So G0 of x has a simple 0 at d. The G0 of x is x minus b, g of d is non-zero. And G1 is L times g of x plus this, where L, so this G1 is not the derivative of G0 in general, because of this L. L is the multiplicity of d as a root of the original polynomial f. But this is still the form of G1, and if you evaluate this at d, it's non-zero. So G1 of d is non-zero. So that means the sign of G1 of d is the same as the sign of G of d. So why is that? It is certainly the same as the sign of G1 of x on the 2 adjacent subintervals. And I had a reason I wrote this without an explanation because it was too obvious. The sign of G1 yes, sorry. So G1 of d is L times G of d, and L is positive. So G1 of d and G of d have the same sign. And because G1 of d is non-zero, G1 of the sign of G1 of d is also the same as the sign of G1 of x on the 2 adjacent subintervals. Now, if you look, so that's G1. What about G? If you look at the interval to the right of d, that is x greater than d, when x is greater than d, x minus d is positive. So the sign of G0 is the same as the sign of g of x, which is the sign of G1 of x. And on the interval to the left, that means if x is less than d, this is negative. X minus d is negative. So the sign of G0 is the opposite of the sign of g of x, and it's the opposite of the sign of G1 of x. So there is a sign change for G0 of x and G1 of x for x less than d, but no sign change for x greater than d. That is, as you cross the line d, this variation of sign function decreases by 1. So the difference increases by 1. The left minus the right sign change function increases by 1. So because the number of sign changes of the sequence is constant for all x, it follows that Vg of x decreases by 1 as x moves from left. So it follows that Vg of x decreases by 1 is x moves from left to right over 0 f of x, and that's the proof. I mean, that's, again, I can never follow proofs in lectures, so I kind of apologize for giving the proof. And maybe I just needed to write it down, so I had it written down. But
Well, I'm not guaranteeing that we've checked every detail of yours, but you got this off of Van der Waerden, right? More or less.
oh, absolutely, yeah.
And
But and you will find similar proofs, I believe. I mean, I looked at Dixon's theory of equations. I looked at Lang's algebra. The only difference, like Lang and there are two guys who've written an algebra book, which a lot of graduate students prefer to Lang, Dummett and Foote. And so they have a different way of doing, a slightly different way of doing Sturm's theorem. They define sort of the general class of sequences that you can construct for the Sturm sequence. And so there's like an added generality in the proof and an added difficulty in the proof, but no difference in the statement of the theorem. So preferring simplicity, and I call this Van der Waerden's proof because I read it in Van der Waerden. And this is definitely not the proof Van der Waerden invented. I mean, I'm sure this was around for 100 years. Well, Sturm wasn't 100 years earlier, but it's certainly, I'm sure it was a standard proof in every European, American, every university, everywhere. I mean, just wherever you find a proof written down. Oh, that's it. Thank you. I'm done. Good for me. Stop share. Okay.